Welcome back to Mathematics 2. Today we are going to have a closer look at optimization, and specifically we will be concerned with constrained optimization today. So while in the past we have usually tried to find local or global minima or maxima of functions that were defined on R to the n or a somewhat restricted set of R to the n, today we are going to deal with function optimization over a restricted feasible set. And that feasible set is usually defined in terms of equations, equalities, or inequalities. Now, constrained optimization is something that turns up very often in practice. For example, imagine you want to make a purchase decision. You want to decide what goods to purchase and in what quantity. And usually your budget for this decision will be limited. You don't have an unlimited budget to purchase goods. So there's your constraint. You have to obey these budget constraints here. Or say you have a company that's producing goods and you want to know what production schedule, what production plan is necessary to maximize my revenue. And of course, the production that you can realize is subject to limited resources. You only have so much labor available, so much capital. You have machines that will limit your production capacities. And of course, there's the market that might not accept unlimited products, or the price might go down if the supply is too high. That's also things that you have to take into account. Another example is you might have control over a certain production process, for example, in a chemical plant. And there are a number of parameters that you can influence for that production process. Depending on how you set these parameters, production might be more or less energy efficient, for example, or might produce more or less pollution. And of course, you want to minimize the pollution, or you want to maximize energy efficiency. But the controls that you have are only within a limited range. Like a chemical process might break down if you supply not enough energy, or if you don't supply enough of certain chemical products to work with, things like that. Your controls are usually limited, and that constrains your feasible region for the optimization process. And of course, there's lots more. Yeah. For example, one more example from physics. Say you have a charged particle that is moving in a magnetic field. And as you might or might not remember, the movement of charged particles in a magnetic field is constrained usually to a circle, depending on the characteristics of the field. But for the simple characteristics, that will be a circle. So you can either incorporate these restrictions into your system, or you can just say, well, I've solved this. I know about the motion. I know this particle will revolve around a circle in my system. And now I'm going to optimize something constrained to this circle of the particle. So that's a number of examples for why constrained optimization might be important in practice. And in this video and the next few videos, we're going to talk about solution methods for these constrained optimization problems. You have probably met that in the form of linear optimization already. That's a specialized tool for optimization that can be described by linear objective functions, and where the constraints can be described by linear functions. In this case, we are going to go for general functions, so possibly we'll have nonlinear objectives, nonlinear constraints. And we're going to see how you can solve these problems, at least under a few circumstances and a few additional restrictions that you might have to impose to actually get a solution method. Okay, so this constitutes a new section that is 14.4, constrained optimization. And I've already said this, but let me just take note of that again. In practice, we're usually faced with a number of constraints on the feasible set of a function. So in practice, for optimizing a function, there is usually a number of constraints on the feasible input values. And of course, we'd like to determine the minima or maxima of a function inside of that feasible set. We would like to compute minima or maxima of a function subject to these constraints. A few examples of possible constraints. I've already talked about those. So one could be purchase decisions, subject to budget constraints. Another could be revenue maximization, subject to resource constraints. And as I said, for resource, think things like labor, capital, available machines, and so on. Or also energy efficient production, subject to limits on the controls of your production process. I will see some of these examples in more detail later on when we apply our theory to examples. Now let's first have a look at the general setting here. How are we going to model these problems? So we have an optimization problem, and usually we want to minimize. Of course, you can also maximize by just minimizing minus the objective. So maximization and minimization are basically the same thing. You just have to flip a sign somewhere on the right place, of course. Okay, so we just deal with minimization formally, but you can easily convert these theorems to maximization settings. So let's say we minimize a function, and we call that function f of x. So that's going to be our objective function. And f is going to be a function defined on r to the n, or a suitable subset of r to the n that maps to the integers, to the reals. Of course, we need real numbers, not vectors, to be able to define what a minimum or maximum of a function actually is. And we want to minimize that subject to a number of constraints. And we sum up these constraints in a different function. We'll call it h. And the constraints will all be written in the way h of x is 0. And h is a function that's also defined on R to the n. We need the same feasible input set. And it will map to some R to the L. So h of x is actually several functions, h1 of x to hl of x. Yeah, so that's a vector. And each constraint corresponds to one of these functions. So we just have to formulate our constraints in a way such that they can be expressed as a function of the input is equal to 0, or several functions of the input are equal to 0. You will notice this does not include inequality constraints right now. Of course, you know ways how to deal with that, but we will explicitly include inequality constraints in a more advanced version of the theory to come in one of the later videos. Okay, so that's our optimization problem for now. And we'll also define what we'll call the feasible set. And we'll define a little more, so let's denote a quick definition here. So we'll have functions f, r to the n, to r, h, r to the n, to r to the l. Define an optimization problem of the form, and we'll just write that once more. Minimize f of x subject to h of x equals 0. Then we'll define two things. The first is we'll define what we call the feasible set. F, capital F, defined as all x in R to the n where h of x is equal to 0. Is called feasible set of the optimization problem. And we define something that looks a little strange at first, but I'll explain that in a minute. So we'll define a new function. The function, we call that L. Now L, that will be a function defined on R to the n, mapping to R. And it'll be defined as L of x equals f of x plus h of x transposed z for some vector z in R to the L. That function is called Lagrange function. Of the optimization problem with Lagrange multipliers Z. So this vector Z is called the vector of Lagrange multipliers. So what does this function do? Well, what we have here is basically a different version of the objective function. So we have the objective, And then we're adding this term here. Let me write that down again so I can make some remarks here. Okay, so we have f of x and then h of x times z. Now, if we have a feasible point, then this h of x will be 0. So this is 0 for x in the feasible set. So for any feasible point, the Lagrange function value is exactly equal to the function value of f of the objective itself. So instead of minimizing f, we could also minimize the Lagrange function. What do we gain by that? Well, if we have a non-feasible point, then this h of x will not be 0. So that's unequal to 0 for x not in f. And that means with the right choice of z, we could penalize such things like having a non-feasible value, right? So if one of these hi, of these constraints is not satisfied, not equal to 0, then it has, let's say, a positive value. And if we set the corresponding z value to also a high positive value, then this deviation from the feasible set will be penalized. So the idea is, if we are able to find good values for that set that penalize deviation from the feasible set sufficiently, then we might be able to get away with just optimizing this Lagrangian function, and we'll automatically get an optimum of f over the feasible set. Because if we would obtain a point that's not in the feasible set, then the penalty would be so high that it could not be an optimal point. Of course, the problem here is there actually a good setting for z, and how do we get that? And what happens here is the theorem of Lagrange that we'll see in a minute, that tells us, well, there is actually a good setting for that set. And there are ways to get that setting under certain circumstances. And we'll see more of that in the examples later on. Okay, so that's the basic idea that we are following here. We look at that Lagrange function, and we want to optimize that. And if we optimize that Lagrange function, basically what we have to do is we have to find stationary points of that function. So a stationary point of the Lagrange function, that's the same thing as a stationary point of the function f of x plus h of x transpose times z. Z is a constant. So we just compute the gradient of the Lagrange function. That's equal to the gradient of f plus the Jacobi matrix of h times z. And that is what we want. So we just take a look at this function here. This one. We find stationary points of that function. And we find a corresponding good setting of that z vector. And if we are able to do that, then we have found an optimum of the constraint optimization problem. And that is what Lagrange's theorem, or the theorem of Lagrange multipliers, guarantees us. That's the central theorem in this video. And let's write that down. So that is the theorem of Lagrange multipliers. Okay, so as always, we won't restrict that to functions that are defined on R to the n, or that are differentiable on R to the n. It's sufficient if the functions are defined on an open set, part of R to the n, and differentiable there. So we just say that x be a subset of R to the n, be open, f defined on x mapping to R, and h defined on x mapping to R to the L. be continuously differentiable on X. So you want those to be continuously differentiable to be able to compute the gradient and the Jacobi matrix. Okay, and then we consider the constrained optimization problem as above. The problem is minimize f of x subject to h of x equals 0. So we have a problem with feasible set f defined as all x in x where h of x equals 0. And there's one more condition such that the theorem works. We need a condition on the Jacobi matrix of H. So let's add that and let this Jacobi matrix JH of X, that's a matrix in R to the L times N. We need that to have maximum rank. And that means the rank of that matrix JH of X should be equal to either L or N, whichever is smaller. That's the maximum rank the matrix could have, and we needed to have that rank. We cannot deal with a matrix that has smaller rank than that. Okay, we need to have that rank for all x in our domain capital X. And then the following is true. If we have an extreme point, then there exists Lagrange multipliers such that the optimum is actually a stationary point of the corresponding Lagrange function. So if x star is in F and an extreme point, of F over the feasible set capital F, then there exist Lagrange multipliers Z star corresponding to that X star. So that's a vector. Let's call the components zeta 1 star to zeta L star in R to the L. Such that the gradient of F at X star plus the Jacobi of H at X star transposed Z star is 0. And just to formulate that in a different way that might be more accessible, that's the same thing as saying the gradient of F at X star plus, now this Jacobi transposed Z star, that's the same thing as taking the sum I from 1 to L over the gradients of the functions hi at X star times zeta I star. So that needs to be 0. Yeah, so it's almost the same condition as with non-constraint optimization. In non-constraint optimization, we would just have that gradient, and now we just have to add this penalty term for the constraints. But of course, we have to know the right Lagrange multipliers. Okay. So what that says basically is this gradient here, nabla f of x star, is a linear combination of those other vectors, of those gradients here. You can just bring that to the right hand side, and then you can see, well, the zeta I star or minus zeta I star, those are the coefficients that combine this gradient of f out of the gradients of VHI. Okay, so nabla f of x is a linear combination of the vectors nabla hi of x star, I from 1 to L, with coefficients zeta 1 star to zeta L star. And finally, a quick look at what that means geometrically. So what does the geometry behind this condition look like? Let's say we have a function f, and we're looking at the contour plot. So f is defined on R2, so we can have a look at the contour plot in R2. And let's say we have a simple function that just looks like this, yeah? So it's a parabola or something similar to a parabola. So these are the contour lines. And then we have a feasible set somewhere. And let's say that feasible set, that is the feasible set, yeah? Either just a line or everything inside of the line, doesn't really matter in this case. So this is the set h of x equals 0. Well, this here is the function f, or the contour lines of f. Then what happens? We want to minimize f subject to h of x equals 0. So what we're looking for geometrically is the lowest possible contour line that just touches the feasible set like this. Okay, so this here is a touching point. The first time that these contour lines touch the feasible set. Any other intersection with that set will necessarily have a higher function value. So that is the optimum that we want, right? So this is our x star. What we have here is, on the one hand, the gradient of f. Now the gradient of f, it looks like this. Yeah, so it's locally orthogonal on the contour lines. We know that already. And of course, the gradient of h is exactly the same. So we have just this one function here. I'm just drawing that a little beside that point to illustrate that those are the same gradients, up to a scaling factor. Okay, so possibly that might be a little longer or shorter. Yeah, so that is the gradient of h. Sorry. Okay, so what that means is basically the gradient of f is contained in the span of the gradients of the h functions. In this example, we only have one h function, but we could, of course, have several. And then the gradient of f could be in the span that is created by those functions. So that's what happens here geometrically. Okay, we'll see a few examples in the next videos, and then we'll extend our findings to optimization problems with inequality constraints as well. I'll see you in the next videos to talk about these problems. Thank you.